My name is Claes Redestad. I work at the Java platform group at Oracle, where we do work on the OpenJDK in particular to well, improve every JVM-based language. So Scala, etc., that are running on the JVM is benefiting from the optimization work that we are doing, hopefully. Every time we Oracle speakers speak in public, we have to say that everything we are saying is bullshit. So this is that slide. I'll just skip through it. So in this talk, of course, the subject of scalability is a broad topic, and I'll try to dive into a little bit of war stories about how to make the JVM better at vertical scaling, both for scaling more tasks in the same VM, and scaling for applications that have larger memory requirements, so scaling up memory, etc. I'll do a little bit of benchmarking using the JMH benchmark harness, and if nothing else is mentioned, I have a machine that has 32 hyperthreads to try and show a little bit of scaling. Nothing here is to be taken as good performance advice, rather as examples of how a couple of things do scale. So when it comes to scalability on the JVM, there are general class of problems, notwithstanding how to write scalable code, but rather when you have scalable code, there are still some subtle challenges underneath your code that might interfere. We'll look a little bit at that, but also sometimes that scalability can be surprising in some effects. So of course there's that concept of making it all easy to work with. Scala is one attempt to solve that. Java has some challenges, and well, we want to support different DSLs. We want to make Java better. We want to make sure that Scala, Kotlin, all the JVM style languages work better and faster, and make the underpinning libraries nicer for these languages to work with. So let's start with a little bit of example to dive into what I'm talking about when talking about scalability, or like when I'm benchmarking things and finding problems in Java in general, or in JDK in general, or in code in general. So this is a JMH benchmark showcasing use of a really old, really bad API point in Java, the Java util date API. And this particular constructor that takes a year, month, and a date, well, it transforms that day in some way to a date point, which is basically a well, milliseconds since the epoch. So that shouldn't be too complex to run, but you realize if you run this little benchmark on any number of concurrent threads, the benchmark doesn't scale. You'll see that the operation, or time to do the operation, increases the more threads you throw at the problem. The reason is simply you have shared mutable state that you synchronize on. I like that we're at a conference here, that this is probably something that is taken for granted, that shared mutable state is the killer of scalability. But well, I like to work with examples, so there's that. Modern Java, of course, has new improved libraries that allow for much faster Java 8 added the Java time API that adds immutable classes that are much faster to work with, translate back and forth between date notations, and simply just scales better. We only see a little bit of drop off when we're above 16 threads here on my 32 core system. That is. So that kind of starting example of where core library changes is being done to support better performance. And of course, these kind of things underpin the Java util date example might be something that no one uses today, but I fixed a bug in the JDK libraries that was causing that particular kind of scalability, or that specific scalability bug in parsing jar files and zip files, which we do at every JVM startup. So that's a nice thing to get rid of. Sharing effects are, we are all running on multi-core systems, which has a complex cache model. We have applications mutating memory or storing to memory that might be used and shared by or read by other threads on other cores on other sockets. So, as an example of a little performance regression that snuck into Java 9 during development, there was this well-meaning little stylistic cleanup to the hashcode method of the string class. So strings in Java are ostensibly immutable classes, but they do have a little bit of mutability by means of a cached hash value on the string object. So the original implementation looked like on the left. We took the cached hash value and evaluated it. If it's 0, we assume that it's not been calculated, and then we go in, check if the car array that we are looking over is longer than 0. We do the calculation. The calculation is mandated to look or do this particular algorithm by the Java language specification. So the cleanup does the same thing, right? The cleaned up little shorter version on the right-hand side. Well, turns out to not really be the case. Can you see what the difference is here? No, we don't have time for rhetorics. So the problem was and is that the store now always happen for the empty string. So if we have the empty string, we always calculated the value and stored the value to the caching field. So for benchmarks, which do a lot of hashing on strings and store this value, that turned out to be a real problem. We lost like 5% regressions in a large percentage of our industry standard benchmarks. And analysis showed that, well, if we guard that store, checks that we are actually calculating a value different than 0, so that we're not storing 0 into 0, that's kind of useless. Then that recuperated our performance. You could look at using JMH. You could look at hardware counters easily to take the normalized perf hardware counters for these methods and show that, well, I didn't have time to fit in the source code for these benchmarks, but they basically run these hash code algorithms on the empty string in particular, verifying that, well, the degenerate regressed case in the middle, our second implementation, where we regress the operation time on quite substantially. This is run on my laptop, so it doesn't show the effect as horrible as it is on a dual socket system. Here we only see that it's grown by a factor of 6. I would think we were around a factor of 100 plus on a dual socket machine here. But we can see by hardware counters that cache misses are through the roof. Well, we see the discrete jump in stores to the L1 cache and such. So having a 500 or 400 fold increase in L1 cache misses is naturally not what you want to see in your application. So this is, well, I would construe this to be an example of true sharing. You have two different threads storing mutable state to a value that both threads are looking at. So it's usually something that you can analyze in your code and see that, like, oh, here we're doing something not very good. We fix that in code. So this was caught by our regression tracking, so never hit a Java release, thankfully. But there's another type of sharing story that, well, in this example, when we got a new batch of multi-socket machines back in 2012 or something, we started seeing curious effects in benchmarking, where benchmarks that were very stable on single socket machines started intermittently or randomly regressing 10%. And this happened more or less stochastically from one build to another. And, you know, innocuous code changes made the benchmark just regress 10%. So this and then months later we found that we could actually reproduce that on the same build just by changing the command line. We were doing performance experiments at the time, adding tracing, adding whatever. So like, oh, this should have a performance effect, but I actually got 10% better performance. Well, analyzing this is not as easy as I would like to say to you, but we finally zoomed in on a possible root cause, and it turned out that all the intermittently regressing benchmarks were running the parallel GC process algorithm, and it has a PS promotion manager, a little object that has metadata for each GC thread. Each GC thread is allocated at the same time by the hotspot VM and allocated in an array, and it lays out its little metadata objects next to each other in memory. Oh, that's raised a few warning flags. So turns out, well, in most cases, and most OSs or most, well, when we were lucky, the PS promotion manager objects were laid out so that they didn't interfere, or they were, you know, lying on a unique cache line. But sometimes they didn't, and that's when we got the 10% regressions all of a sudden. So what happens here is when well, you're having a very mutable state, it's supposedly not shared between threads, but since they are laid out close to each other in memory, and sometimes, you know, cross cache line boundaries, then writes by thread 0 to the PS promotion manager for, well, its own data, it's caused cache eviction of the neighboring PS promotion manager. So that when that thread comes in, it faces a cache miss, has to load data from memory, and well, we don't want to load data from memory more often than necessary. So this well, this happened implicitly. You couldn't do anything about it in your code. This is down in the GC, and you got randomly on anything, well, any version of Java or the JVM prior to 6 prior to 8, I think we fixed this in. You could run into this problem. There was really nothing to do. So false sharing, for those unfamiliar with the concept, is when you have this, well, basically what I've said. When you do stores, you'll have a cache coherency protocol engaged by the CPU, depending on the atomicity guarantees that you're requesting. If you're doing release acquire semantics or whatever, it might incur further cost, but even if you're not doing atomic stores or reads, you'll still engage a protocol that will saturate and use cache coherence traffic between cores and in many cases between sockets to check that other cores aren't using memory that is being mutated by other threads on other cores. So also since this is a hardware-related problem, when we move from a single socket machine to a multi-socket machine, the latency costs involved grow. I don't have the exact cost factor, but it's definitely orders of magnitude. Now, the solution to to false sharing is often to try and combat the cache locality of your memory. How to do that? Well, the brute force and simple technique is to pad your data, make sure that data is cache aligned, or if that's not possible, make sure that there's empty data before and after the state that you're updating, to make sure that you're not interfering with contended or highly mutated data next to your memory. Well, for good measure, we also align the array to make sure that objects start at cache line boundaries. And this has more or less removed our performance woes with the parallel GC to have very inconsistent scores from run to run. However, this is a case where false sharing was extremely noticeable, but because we were doing something massively parallel, every thread on the system was basically hammering on these mutated states, and it caused long pauses. But it's not unlikely that there are other problems like this all across the in the native implementation of things and in user code, etc. But it's simply harder to detect it when the contention isn't too high. It's easy just to disappear into the noise, but then it might come back with next generation of hardware. You get more threads, you get more sockets. Then the problems or hidden scalability bugs will crop up in places, and this is why we are always requesting more hardware budget. But anyhow, so contention then. I mean, we have these kind of contention issues with false sharing. We have contention issues sometimes. We preach the gospel that we shouldn't have shared mutable state, etc. But sometimes, even in code, even in an application that does everything right, you have to synchronize, do handoffs between threads, or you have to your actors actually have to pass the message or whatever. And sometimes there's need to use synchronization primitives. So for Java 9, we did a lot of work to improve the synchronization primitives in the JVM. Well, there's basically very many or 3 different locks. You can ignore the thin locks. So we have either bias locks or heavy contended so-called monitors. And the biased locks are basically for the happy fast path, where we need to synchronize on a Java object, but you're the only one doing that. For example, you have a thread local string buffer or something like that, and your data types just happen to be using lots of synchronization. Don't do that. Then bias locking is the optimization technique to make sure that the overheads of synchronization on those kind of uncontended cases approaches 0. The heavy monitors are like the full-flown synchronization primitives for when an object is actually contended. There's more than two threads competing to be the one to lock on something and synchronize on something. And we use the term that when something needs a full-blown monitor, we inflate the object. So we take a monitor from a native queue of monitors, and we install it into the object header. Did I mention that all object headers in Java are mutable? Oh, damn it. So this causes lots of problems with cache eviction, false sharing in the monitors themselves and in the objects themselves. So while the JEP work did a lot of very nice little optimization to reduce latencies in synchronization, of course there was also false sharing discovered and improved in this area. So we've lately seen that everyone wants to use padding to ensure that we eliminate false sharing sources. I'm a little bit worried that we've gone overboard with this, so more and more data structures in the VM are now being padded and are becoming heavy in footprint ways instead. But in targeted microbenchmarks, we can see that worst case latencies for synchronization in JVM-based languages have dropped tremendously in Java 9. This was also applied to internal mutex monitors in the used by the VM native VM itself, and since 8 we also have a little internal annotation to do this kind of tricks for Java fields and classes as well, although it's not been exposed as a public API. Maybe that will happen someday. Right. Locking and stuff is interesting. You have programming models, but you also have, when running anything on the JVM, you have a problem with a few inherent latencies being brought on you by the inner mechanics of the VM itself. Everyone know of garbage collection, but there are costs involved in even setting up the system for doing a garbage collection, which is something we call save points. So when we need to stop the VM for any reason, or stop the application threads in a JVM for any reason, for example, to do a garbage collection, we need to do a stop the world collection. Hopefully we shouldn't have to do that very often. Then we currently take a save point, and that, well, the GC subsystem requests a save point that make more or less signals to every application thread to stop and let the VM do its thing. And this is done by, well, there are a couple of different techniques that you can choose between, but it's basically every JIT compiler, every interpreter, etc., are emitting these polls at regular intervals to make sure that Java threads are checking if they should actually be allowed to continue work, etc. So there are latencies involved in that. I mean, you're interpreting bytecode or you're executing native code, and you want to do that as much as possible. And sometimes you even optimize that, like, oh, how long can it take to iterate through a million step loop? Let's just do that without checking save points. So there's kind of like an unknown. Your application can be pessimized by neighboring code, etc. Because when save points happen, and they do happen, there's even a diagnostic or there's even an option that forces the VM to take a save point every second. You can of course tune that to be a much lower value, or implement a GC, for example, that doesn't have to. Anyhow, well, save points are and the latencies involved are generally small. I mean, there's the time to do this or to initiate the save point. There's time to do whatever work is being done there. Sometimes it's GC, which depends on your GC algorithm. Might take a long time, or it's a good, or it's a good GC and it takes reasonable amounts of time. But working on the kind of like superscalar GCs, we realized that other things that were happening in save points were actually starting to not dominate, but take so much time that they were certainly affecting our bottom line when it comes to scalability. And one such operation is the circling back to the monitors. When once monitors have been inflated and added into installed into objects, they aren't deflated by themselves. Rather we have to scan at save points when everything has been stopped, whether or not the monitors involved in locking certain objects are actually needed anymore. Because, well, and if they are not needed anymore, they should be reclaimed. And this little operation was done at save points, and is being done by save point by a single thread, scanning the entire population of monitors. And in certain applications, we can see we can certainly see that the population of monitors grows to a factor 1,000 more than the number of application threads in the VM. So if you have, say, 10,000 threads, you'll have 10 million monitors, and all of a sudden you'll see up to, depending on hardware, maybe 50 millisecond pauses just to scan through the population of monitors every time such scanning is deemed necessary. So these kind of like 50 millisecond pauses that come from nowhere and isn't seen in GC logs, etc., surprised everyone. And turns out there was actually a few optimizations done back in 2010 to reduce the number of monitors that we look at, but it never occurred to anyone to make that optimization default. We made it default in YAML 9, so now we at least do an optimization to only check at monitors that are actually installed and in use by someone, which reduces, on average, the number of monitors that we check by a factor of 1,000, which reduces certain save point related pauses from maybe 50 milliseconds to a fraction of a millisecond. Anyhow, still, this has spurred some work. I know a few people, engineers at Red Hat, are looking to turn this into fully concurrent operation that can be done without save pointing, or do parallelization of this kind of cleanup task. There are other tasks than monitor deflation, of course. I'll not go into details on those. Another approach is to optimize the save points themselves. Why are we stopping all threads so often? The JVM has a bad habit of forcing every application thread to grind to a halt, do some cleanup and stuff. So for Java 10, there's been some work spawned by the VM team here in Stockholm to allow more tasks, or certain tasks, to use so-called handshakes, which allows for targeted, like this thread or this application thread is signaled to do a certain task, and it allows for tasks like bias locking, revocation, and such. It allows for doing instead of waiting for every thread to halt and yield to the VM thread that is going to do the save point. It allows for individual threads to stop individual threads. You don't have to stop all threads. You can more surgically realize that certain tasks like bias locking, revocation can be done on the individual task. You don't have to stop the entire VM. The infrastructure is in place. We haven't really implemented any application where we are stopping individual threads. But it also turns out that this mechanic was good enough to kind of replace the global safe pointing altogether, and it has some, it doesn't really. So it seems like we can actually clean up the global safe pointing as well. A spin-off of that is other optimizations for example, when threads transition from Java code to native code to VM code, we have memory barriers that or mechanic for memory barriers to make sure that memory barriers on a CPU level make sure that you force the CPU to not reorder reads and writes before and after certain kind of memory barriers or fences, and such fences are laid out well in certain places more often than otherwise. And back in early 2000s, Dave Dice of Sun fame implemented an optimization that allowed us to avoid using hardware fences for doing these kind of membar transitions. So when we transition from Java to native to from native into VM, etc., we could avoid doing expensive and heavy fences. This has turned out to be a problem. On modern hardware, the cost of fences has shrunk, but as we scale up to more and more threads, having accidental global synchronization between threads or global synchronization between threads is problematic. And this pseudo membar implementation was doing that kind of. It had to flush the thread state of all threads to make sure that they are not doing, that no thread is reading, writing to memory that my thread is interested in. So when my thread is doing a transition, I had to synchronize with all other threads. That doesn't scale very well. And well, turns out that the minus use membar optimization also had a number of bugs related to it, and also possibility of false sharing when number of threads grow above 64. So even though there's been some complaints that we are regressing a few local micro benchmarks with this change, we are seeing huge improvements on large systems with simply using a simpler algorithm, because hardware has caught up with theory. Thanks. Right. So SafePoint and other such latencies are a problem that we are, looking at in detail when those kind of latencies happen to you or happen to code, whether or not you want to. And then, well, GC is one of those subjects that we always get back to in JVM land, because well, as we have garbage collection, that becomes a problem for many users, many applications as we scale up. For many small devices or small applications, GC is a little bit of a solved problem, but the real challenges are when we are scaling up the memory requirements. When we're scaling up applications to terabyte size, and finding that applications or subsystems in the GC were not scaling as well as we had thought. Things that were, blissfully humming around at maybe a few hundred milliseconds of pause times on a normal heap. By normal, I mean like 32 gigabytes. On terabytes, that's we got like concurrent marking, only to initialize what was supposed to be a concurrent process took 15 minutes on this particular customer, which meant that the concurrent marking that's supposed to be happening, while the application is running, it never even started before the user ran out of memory and had to do a full GC instead. So having restructuring, key data structures in G1 for in the performance work leading up to Java 9 caused some pretty severe or pretty impressive scalability improvements. This is quotes from a customer that has made a talk at Java 1 that has seen for the first time that they can actually run with a 10 terabyte data set with a concurrent GC that allows them to have reasonable pause times. So of course they could run with a parallel GC and get reasonable throughput, but then they were facing many minute pauses every now and then. With G1 they can now actually run with mostly concurrent garbage activity. Means that stop the world phases are rare, and if they happen they are just below seconds. But still some people don't think that some second pauses are good enough, so we have a couple of engineers at the Stockholm office that are working on a really cool alternative GC algorithm that promises sub 10 millisecond pause times even on multi-terabyte heaps. And this is not only vaporware, but we don't have really any technical previews to show you. But ZGC, well, there's other technology worked on by Red Hat, the Shenandoah GC. They do overlap a little bit in goal and where to be applied, but they do go about these things a little bit differently. And I know that Shenandoah has been pulling back a little bit on their maximum pause time goals. I think their current official statement is 200 milliseconds, which is not that much better than what G1 can achieve. Yeah. Okay.
I was wondering if they're related to the Azul C4 collector, which uses both the read and write barriers.
Right. So I think the ZGC tries to only do read barriers. So it tries to only make sure that writes are always happening in a fresh region. So it can elide a lot of write barriers. So it allows for scalability in that sense. But that's a pretty. So there's a project proposal which goes into a little bit of details. There's code that's going to be published very soon. It's going to be open source if it happens. So yeah, this was a very secret source project for some time. We were like, some people were banking on making this a commercial feature and something that we could make big bucks on. But as some of you might have heard, Oracle are moving to take all our commercial features that we are building onto the OpenJDK and making them open source. So instead of just letting ZGC go to the garbage bin, we're contributing it to the OpenJDK. Right. So of course, like a GC algorithm like G1 gives you reasonable throughput, it gives you reasonable pause times, etc. It's a jack of all trades GC. Something like Shenandoah and ZGC that are targeting very low pause times for very, very high scalable heaps. Of course, there has to be a trade-off somewhere. Trade-off might be footprint, it might be throughput reductions. You might have to change the way your GC workers go about doing their thing so that they try to get cache locality all the time, etc. I didn't understand half of it, but Stefan Karlsson at Hotspot was up in arms about the striping feature that does smart cache local NUMA-aware things to keep memory grouped into tighter chunks and make sure that GC workers are smart about which chunk of memory that they are working on at the same time, which does wonders for latencies of those very few stop the world pauses that still happen. But most and everything is being done concurrently, and you just limit what you're doing in stop the world phases to the bare minimum. And of course, to do that, you'll have to do things to organize memory into or data structures, etc. That sacrifices footprint, throughput, etc. for the benefit of low latencies and thus scalability. Right. I'll just finish up with an honorable mention that, well, we mentioned that Java threads are a resource hog, and we have a really exciting project called Loom that aims to implement coroutines natively in Java. It has, dissertations on fibers, coroutines, where you have green threads that are very lightweight user mode threads, remove penalty on blocking on these kind of things. Support tail calls, yay. So Ron Pressler, relatively recent hire, he's been with us for a year now, I guess. He has written a few pretty cool libraries in Java called, for example, Quasar, and the goal is to allow for a new and refreshed threading model for the JVM, which should benefit all JVM languages as well. Right, I'll stop there and ask if there are any questions.